All right. So I should be live here. We're going to have to see if this spools up correct and if everyone can hear me and see me. I'm looking at the chat here, so if you can hear me, if you can see me, let me know. Give me like a thumbs up or a thumbs down, I guess. And let's make sure that we're all on the same page before we get things going here. All right. Looks like people can see. Keep an eye on the chat here. Thank you all for joining, by the way. There's a bunch of you here. It should be a great presentation. We're going to talk about some fun stuff. I'm going to try to keep it like a good balance of cool footage and fun data to look at. And it's great that like a bunch of people can join this year without having to buy plane tickets or hotel rooms. That's a silver lining of this strange NARCON. But I guess if everything looks good, sounds like everything's good here, we will get started. So what I'm going to do is I'm going to share my screen. Here we go. Here's screen. I'm going to share the whole thing. And it's probably going to look a little weird for a second. So screen sharing, and then I'm going to start the presentation. And I've got, let's just make sure that everyone can see here. Little technical difficulties. If you can see the presentation, yep, here we go. Looks good to me. So if we are all set, right before we get started, my plan is I'm going to run through this, and if you have questions along the way, there's a little Q&A tab. If you look at the top of the chat, there's a little Q&A tab. You can also put stuff in the chat if you have comments or just stuff you want to say. And we'll do a big Q&A thing after this. I'm going to try to cover as much as I can, but if you're confused about stuff, put it in the question or put it in the chat, and I'll try to get to it. So let's get started. We're going to talk about the rocket that is actually sitting behind me. You can't see it very well in this shot anymore, but it's the one that's in these photos. It is a propulsive landing model rocket. We use two Estes F-15 motors. This thing is about 1 meter tall, 66 millimeters in diameter, very, very tiny. But let's get started here. So first, what I want to do is show some footage so you guys can see what this is. You may have seen this on YouTube, but if you haven't, this is played back at quarter speed. Let me hide this little thing. No, that didn't work at all. Oh, no. Oh, no. What have I done? Oh dear. Okay, let's try this one more time. So here we go. Sorry about that, everyone. Hopefully that's the only hiccup. So this is Scout E. I've built a bunch of rockets over the last 5 years that I've been running this BPS program. And Scout E is the latest iteration of this design that I've been working on called Scout. So we have Scout A, B, C, D, and now E. This is flown in November of 2020, so just a few months ago. We go up to about a 30-meter apogee. The rocket weighs about 1 kilogram. After apogee, it pops fins out and it ejects one of the motor cartridges, this little Estes F-15 motor, and then it comes back down and does its best to try and land propulsively. And of course, as we've seen with vehicles big and small, it doesn't always go perfectly. So this one has a lot of slide on touchdown. We get pretty good with the altitude, a little bit of a hop at the end there, and then you can't throttle these motors, so you have to get it pretty close. Now, you kind of can throttle these motors, and we'll talk about that in a bit. But this is Scout. We'll have a lot of footage to review here, and I figure one way that we could talk about this is to address like different sections of the flight at different times. So first, we'll start by talking about the physics of how this works to sort of prove that it can. Oh, it looks like the frame rate's a little low on this. Hopefully that's okay. Well, we'll keep pushing forward here. So we'll start by talking about the physics, and we'll go into the things that we need to control about the flight. We'll move on to the mechanics, like how we do that control, the electronics, the things that send the signals to that control system, and then finally the code, how the flight software is set up. And so we'll try to address all of these things, and then we'll do questions after. So starting with the physics, I consider this to be a sort of momentum management problem. And we'll do a quick example in a second, but on the left, you see a photo of two Estes F-15 rocket motors. I do want to address that there is an igniter in one of them. This is taken on the day of launch, and you have to preload that landing igniter before you fly this thing. So to be perfectly clear, the leads on the end of that igniter are twisted. It is unable to fire, and that isn't armed until about 10 minutes before launch. Yeah, so we've got these two Estes F-15 motors, and one of the remarkable things that Estes has done, whether they meant to or not, is create an incredibly consistent burn profile. So on the right, we've got a plot with newtons on the vertical axis and time on the horizontal. So it is a 3.5-ish second burn with an average of about 15 newtons. So this is data captured from actual flights. This is data captured from, what do you call it, like a test stand with a load cell. So this is, and it's flown in multiple environments. These are multiple batches of motors. Their process control on building these things is very good. I know they have a tour that they're doing on Sunday for NARCON, and I'm really excited to see what they show there. But let's talk more about this momentum management thing. So consider the scenario where you're in space, you're in the vacuum of space, there's nothing around you, and we're not going to think about mass, we're not going to think about drag. So you fire one Estes F-15 motor, or any motor, you fire one motor in one direction, right over here on the left, and then you go over, you wait, 2-3 seconds, and you fire a second motor, and assuming the thrust is totally consistent between the two motors, assuming mass doesn't change, and assuming you have no drag, is it possible that that second motor could completely arrest the movement created by the first motor? Put it in the chat, or, I know the answer, and it's probably pretty clear to most of you. But the answer is that, in theory, yes. If you don't have mass loss and you have the exact same thrust and you don't have drag in the vacuum of space, you will arrest that movement of the first motor every time. You'll bring it back to zero for no matter how long you've coasted or whatever. You can put the same, you put some amount of power into the system, and then you take the exact same amount of power out of it by firing the equal or the opposite direction. So now let's add something. Let's talk about mass. What happens if the first motor fires and we lose a little bit of that propellant mass? So now the rocket motor that's traveling through this hypothetical space situation has a little less mass. On the right side, when you fire that second motor, are you going to arrest the movement completely, or are you going to end up going a little bit back toward? You're going to put more power into the system. It's the same amount of power, but it's tough to figure out the terminology for these things. Essentially, if you have mass loss and you have a slightly lighter vehicle in the second scenario, you're always going to put just a little bit better, like a little bit more thrust back into there, and you'd end up going back toward 0.1 on the left here. And finally, if we were to add just a little bit of drag, and this is where you need to suspend some disbelief here, if we were to add a little bit of drag that fights the movement in scenario 1, so, when the F-15 motor fires, it actually gets hindered as it goes up to speed. We're fighting the drag to get going faster, right? That's the first one with the drag. And then we go over to the second half. But when we're starting to slow down, the drag is already helping us because the drag, is taking energy out of the system. So that when we fire that Estes F-15 motor, if we still have the same thrust and we still have that mass loss, we're going to go even further back toward the point number 1 here. So the idea is that, you can try and hide this problem by keeping the scale really small, but this is always going to be an issue. You are always going to have to accept that if you're using the exact same motor, you either have to throttle it, you have to accept some type of hop, or you have to just get really lucky or do something else kind of tricky. So that's the momentum management problem that I'm talking about. And if we look at, this is a very complicated slide, but what we want to focus on here, these are 5 different simulations of a flight. These are not actual pieces of flight data here, but if we look at these 5 separate simulations, you'll notice that on the altitude plots, that's the third from the top here, the altitude plots, if we zoom in, all have that little hop in them. This is just a physics simulation. We are accounting for mass loss, we're accounting for drag, we're accounting for as much as we possibly can without flying the thing. We're always going to have that little bit of a hop. So that's just to get everyone friendly with the idea that, we're going to have to have a little bit of a hop if we don't bleed off the thrust some other way. So, okay, that's the physics part. Let's talk about control now. And specifically, let's talk about the aspects of this flight that we need to control. So the first thing that might come to mind, especially for people, I know there are a couple people in this audience who are doing, trying to do thrust vector control rockets. And so the first thing that comes to mind is your attitude, right? So your angle that the rocket, stays at. You're balancing a pendulum by gimbaling the motor at the bottom. You want to control your attitude. And roll technically counts as attitude too, but I'm going to add controlling roll into this. You could launch and land one of these things without any type of roll control, but it makes the control system very happy to have a little bit of roll control. Let me get this glare out of the camera. The other things we need to control for are velocity, right? So if we touch down and we're sliding, not just talking about vertical velocity, talking about horizontal slide as we touch down onto the ground. We need to be able to control that slide and make sure that we're not going to tip like you see in most of this footage. And by that effect, we want a little bit of control on position. Some of these shots are kind of fun to watch when you can see it coming down on the right. But we want to control position, and then we want to control throttle as well. We need some way to make sure that we can have some amount of control over the thrust. It's going to be very hard to get it just on luck alone, and there's enough that changes with the flight during the flight that you kind of need some type of control over that. So these are your things that you need to control. Okay, let's talk about how you do it. I cannot get the glare out of this camera. Hold on. Let me see if this will help. This might make it worse. Well, okay. I don't know if it's going to get much better than that. So the mechanics, like how do we actually make this stuff happen here? Let's start with the simplest stuff. So let's start with parachutes. Now, you'll notice in the video that I showed, there are no parachutes on this rocket, or at least none that deploy. And so in contrast with most model rockets, we're coming down under thrust. But what happens if you're going up and a servo fails? Or what happens if you're going up and you program something in wrong and the flight goes off course? Or what happens if you try and light the landing motor and it doesn't come up to thrust? These are all bad days. And if you're going up to 30 meters and you're doing it in an open field of grass, like who cares? You're just going to smash the cardboard tube. But, it's experimental stuff. You want to be safe. So I have parachutes that pop out of the side of this vehicle. Side deployment is usually pretty risky if you're going fast, but because we're going pretty slow, we can sort of afford to do this. You can see me experimenting with a couple of different parachute packing methods. This is all shot at 1,000 frames per second. We put a gratuitous amount of black powder in this little compartment to get the parachutes out, and you will probably not be able to notice it on the vehicle. It's pretty well concealed. So here's a close-up shot of it. This faces towards the back of the launch pad, and so there's a bunch of abort criteria that we can talk about later where you can imagine if the rocket's coming down and for whatever reason it's totally sideways, parallel with the horizon, if you fire that landing motor, you're not going to be able to get your rocket to, pitch back up in time and spend the right amount of thrust in the right directions. So there are scenarios where you want to use these parachutes, and so each flight has those armed and ready to go. Moving on with mechanics, we can talk about landing legs. So the stuff on the bottom of the rocket, these are 2mm and 4mm carbon fiber struts. They are solid rods. They're terminated by little PLA 3D printed joints and then epoxied together. So dialing these in was really difficult. We actually had an intern at BPS over the summer who did the majority of the design work on these. But you can sort of see how it works. The leg ends up overextending, and because the carbon fiber has a little give to it, we can overextend the leg and then have that strut slip into place and then be retained there. Took a lot of dialing in to get this right, but the huge benefit of using really stiff materials in compression that specifically, like carbon fiber, is that there is very little bounce. So I'm not sure how well it's going to translate with the frame rate on this presentation, but you'll have to just take my word for it that as this vehicle is dropping down onto the hardwood floor, there's essentially no bounce. And as it turns out, all of the bounce in these flights seems to come from the sponginess of the grass at the launch site. So we can talk about this a little later, but we still have to work out some of the bouncy problems with some type of crunch zone or something that can absorb the energy without putting it back into the system. Okay, This one's going to have to play a couple of times, and I kind of imagine it's going to be tough with the frame rate as well. But this is a roll wheel that's inside the vehicle. So on the bottom right, you're looking at the top of the flight computer. There's a little tiny wheel that spins up and spins down depending on the roll angle or the roll attitude of the rocket. And so what we're doing is the same way that a lot of spacecraft will change their orientation over time, is we spin up or spin down that wheel to exchange the momentum with the rocket. So if the rocket rolls one way, we can spin up the wheel and sort of correct for that. Again, not totally necessary for this, but it does keep the control system really happy if we're not spinning very fast. On the top right, you can see the plot of the roll wheel as it tries to control the orientation. We don't even need to spin it up on Ascent, which is interesting. We just don't even get like any roll torques on the Ascent of the flight. Okay, cool. So that's roll. This stuff is really cool. These are the fins up top and how they work. I'll let this play a couple of times as well. So the fins are printed out of polylactic acid. This is probably objectively the worst way that you could possibly make fins. They're plastic PLA, and so they're extremely flimsy. You can even just see it in the video here. They're very flimsy, so you can't, like, they're not going to put much force into your rocket without bending or a lot of give. But the idea is that I just needed something that could, you know, barely work and correct the flight while we're in an uncontrolled state. So the fins are pushed out with a tiny servo that's up in the nose cone. They're retained in the rocket with a little piece of Velcro that sort of slides against the airframe, the cutouts in the airframe there. And then they are retracted by gravity, by their own weight, because they're just hinged at that one point. And so if we go here, you can see them deploy in flight. Watch this a couple of times as well. All right. Here we go. So the motor ejects, the fins come out at apogee. Here we go, coming down. If you look really close, you can see the fins bend. You can see that when we come up to peak thrust, the fins slightly sag because the servo is actively trying to resist them going back into the airframe, and especially under peak thrust when we're at, you know, it's probably like 2G of acceleration. It starts to push a little harder on the servo. But anyway, yeah, so the fins come out. You can see they definitely work. We would have, without those fins, rotated a lot further in the other direction, and, you know, trying to prepare for the landing burn, we want to be as close to upright as we possibly can. That makes the rest of the flight a lot more predictable. And then we bring the fins back into the vehicle. I'll show some data about this later. The fin criteria for being deployed is anything past apogee, the fins must be open, and anything under 4 meters per second when we're close to the ground. After about 4 meters per second, the fins have very little effect. And frankly, you know, we could put them in the vehicle at this point too, and it would be fine. But that's just sort of how the controls on those work. The thrust vector control mount is the hardware responsible for pointing the direction of the motor. This part is pretty cool, and we'll watch this shot a few times. This is a lot of characterization testing this fall. So you can actually see 2 load cells, if you know what they look like. They're these silver blocks with the 2 hole shapes in the middle. So I'm measuring the thrust of the motor. The other thing I'm measuring is, if you look on the side, one of the pylons that's gripping the rocket, you can see a load cell on there as well. And so when we fire that motor and come up to thrust, we're measuring that side force to like verify that when we go to 4 degrees, we expect to get this much side force in newtons. The load cell verifies that for us. And so you can see it in a couple of these tests. We have 8 degrees of gimbal range on one axis and 4 degrees on the other. And the craziest part about this mount is not necessarily the, it's not necessarily the gimbal range or anything like that. It's that the motor mount can hold 2 motors. Oh, I forgot I put this shot in here. This is a nice little digitally stabilized shot, so it's very rock solid in the picture. But you can see the rocket sort of kick itself over on Ascent to clear the pad for when it's coming back down. Someone suggested I use picture-in-picture, not full screen, for best results. Do you think we should try that? We're doing pretty well on time. It might be worth trying that. in the meantime, I'll keep talking about the motor. So this is the CAD file, the design file for the thrust vector control mount. It looks a little wild and odd, but I'll sort of walk through what's going on here. So there are two motors in the frame. The top one is for landing, right? That's sort of stored in the airframe. The bottom one is for ascent. So that's what gets us up to apogee. On the top motor, there's a little bit of a hat. It's literally called that in the CAD. It's just a motor hat. It's like a little party hat. And the two screws that you see on the side there, there's a set of springs that are constantly putting tension against that landing motor. And so all it takes to get the landing motor into place is to remove the ascent motor. The design I'm quite proud of. Anyway, well, we'll just take a look at some footage. We have to remove the ascent motor to get the landing motor in place, and you can easily see how it happens. When we slam the ascent motor into a rod and slightly bump it out of place because we only have that half circle that's encompassing most of the ascent motor, when we slam it out of place, the landing motor slots into place, and you can see that locking pin engages so that the landing motor can never go back up into the airframe. It took a ton of dialing in to get this right, and you will see footage on footage on footage of how this works. Because it's totally new. I've never seen anyone else do this, and you can imagine how bad the day would be if the flight failed because something as simple as this didn't work. You certainly don't want to fire the landing motor when the ascent motor is in there, and yeah, so there's just a bunch of footage of this. Some of the tests are more successful than others. Again, copious amounts of characterization here. So what I'm doing in this shot is trying to see, like, over multiple motors with slightly different masses, how consistent the ejection forces are by ejecting it upside down. I'm also testing how you can, like, safely mount the igniter in the landing motor and not have it come out during this violent event. This looks very slow and graceful. The problem with this is, of course, it's violent. It's violent as heck. And so I am a little concerned about propellant fracture if you do this with a motor too much. Like, I wouldn't, eject this thing 10 times before you fire it. And there's some, like, it's a little concerning to try and get this ignition cable out of the way. It works fine for the flights, and, like, so much of this stuff is just insanely complicated that whatever, like, let's add more complexity. But anyway, so here's some more shots. One of the hardest things about getting this right was the static friction between the ascent motor and the lip that retains the ascent motor, like the lip that the landing motor slams against. And so here you'll see a failed test where we hit the ejection pin and nothing happens because there's all of that spring-loaded force that's pushing against that lip. So I'm experimenting with tons of different materials in between. A 3D printed surface is not that smooth. Any of you who have tried 3D printing before know that the surface, depending on what the surface is, has all of these little boundary layers, these little ribs on the print. And so if I want to keep manufacturing this part out of polylactic acid, which is really convenient, so I do want to, I had to find some way to make this ejection more consistent. I mean, this looks janky as all get out here. Like, this is sketchy. So what I ended up realizing is, how do you move a heavy object across a flat surface? You roll it. So there's a steel roller bearing that's a part of the design now, and you can see it in this shot a little bit better. We get rid of all of that static friction problem because it's very easy to eject the ascent motor if all of the force is against what is essentially a large, like, as large of a surface area as you can get wheel that it rolls along to eject the ascent motor. And this ended up yielding really high reliability. And you can see there's a bunch of tests with it here. I can't remember how long this clip is, actually. Let's see if anything else comes up. Yeah, I think this might be the last shot in here. But yeah, so you roll it along that little lip, and then it slots into place. Okay. Now we can talk about electronics. Okay. So, with electronics, what do you need to control? Let's think about that from the top level. We need some ability to fire parachutes. Again, you don't want to. but you want to have the safety of doing it the right way. And so part of that is having some backup system in there in case the second motor doesn't work. Excuse me. We need to be able to actuate the upper fins, which could, in theory, be it's not pyrophoric or pyrotechnic deployment. If you wanted to do a one-time deployment, so you need a couple of pyro channels. Same with leg deployment. The way I deploy my legs is they are constantly spring-loaded, and we cut a little nichrome wire or cut a little rubber band with a nichrome wire, and that deploys the leg. So that has to be another pyro channel. We need the ability to control a roll wheel and TVC servos. So those are PWM outputs. That's like a servo, type output. And then in terms of sensors and components, the things we need are, and first and foremost, an inertial measurement unit. So this is going to give us measurements of our gyroscopic rate, how fast we're moving, the angular velocity, and acceleration, linear acceleration along 3 axes. And actually, this is all you need. Like on a technical sense, you only need an IMU and a processor and like well, you need a bunch of stuff. But in terms of sensors, you can do this just with an IMU. If you have good enough like pad leveling, if your vehicle is really, really level before flight and you have very high certainty in your state before you actually launch, you can do it with just an inertial measurement unit. Like I've modeled the noise of these sensors and the inaccuracies. If you're within 0.2 degrees or something, you could do it just with this. But I don't, because that's crazy hard and I just don't want to. So the other sensors you kind of want on something like this are a barometer to measure your altitude. That's going to measure the air pressure. You can correct for any drift in your inertial measurement unit. And I like using a GNSS radio, which is a GPS chip. So people sometimes freak out about having like a GPS on a rocket. And it's like, oh, it's a missile, but there's no regulations that are actually against it. It's all sort of hearsay at this point. But the GPS helps you correct for the speed errors and position errors that you would accumulate really, really fast if you were just integrating the measurements from the IMU. In terms of other things, you're going to need a processor or a microcontroller. And so this is going to do all of the math on your rocket. It's going to try to calculate when you need to burn that landing motor. It's going to run all your code. That's also going to control the servos. You definitely want some type of data logging device. Because if you're doing one of these flights and you don't have any hard numbers coming back after each flight, you're going to spend a lot of money burning a lot of rocket propellant before you get anywhere. So you want some way to get measurements back from the computer. And then finally, a MOSFET is going to be able to drive high current to anywhere in the vehicle. So pyro devices, like the nichrome wire separation stuff. So these are like the basic components. And I ended up designing this computer about this time last year. The computer is called AVA, which stands for All Vehicle Avionics. And it has all of those sensors and more. And sort of the design philosophy by this, it has 3 processors. That's what we're showing there. The design philosophy behind this is I've designed a bunch of printed circuit boards, like way too many. And I was kind of getting sick of it. So I decided what I'll design is one circuit board to rule them all and to be like, everything that I need for the next 2 years. And so that's what this is. It's got an inertial measurement unit. It actually has 3 technically. It has a barometer. It has GPS, Bluetooth, all sorts of stuff. It's a very, very fancy computer. And when they catch on fire or crash into the ground, it is sad because they're also expensive. Okay, definitely not speaking from experience on the fire or crashing into the ground. No, sir. Okay, so now we can talk about software. This is everyone's favorite thing because it's really hard and coding is kind of also hard. At the core of most of the stuff that I build is something called a state machine. And so a state machine is this really powerful way that you can set up software so that you can run isolated chunks one at a time. And they're found in, almost any device that you have. From if you have a smart fridge, it's probably running a state machine in some way. And so an easy way to look at it would be, for this specific flight profile, we have different states of the vehicle where we run different little chunks of code over and over and over again. And that lets us isolate things out. So what states would we have for a rocket like this? We could start with the idle state, so the state where it's on the pad, it's just reading sensors. We could be calibrating some sensors on the pad like constantly, and then we want to detect launch, right? That would be one of the things that we run in this sort of control loop of the state. Then, excuse me, we have a launch state, right? So this is when we're flying under thrust. We're pointing the gimbal mount, we're pointing the rocket motor, we're aiming down range to try and clear the pad a little bit so that when we come down, we don't hit it. And we're trying to detect burnout. So that's the launch state. Then we have a coast state, right, where we eject the motor, we deploy the fins, we start the second burn. I'll grab a drink of water here. Right, so that's our coast state. And then finally, we could have a landing state, which is triggered by the starting of that second burn. We restart the gimbal, we plot the throttle divert maneuver. I can't remember if I talked about that yet. There's like a lot to talk about. We plot the throttle divert maneuver, and then we detect the touchdown, right? So these are all of our discrete states of our state machine. And this is a vastly simplified version of what's going on. So I'm going to play the live telemetry. One of the things that Ava does is beam telemetry back down to the ground. So I wrote it's a telemetry visualization software that shows sort of the state of the rocket and what the flight computer is doing. And so take a look in the upper left of the screen here, and you'll see the state is ready for launch, and then flips to flight vertical. You'll see it flip again to flight pitch kick. So that's where we're trying to head a little bit more actively down range. Then we go to, 1 second, after burnout, we go to unpowered ascent. And then watch when we pass apogee, we go to unpowered descent. Fins come out. And then right here, we should switch to landing burn startup. And right after we start that burn up, we take a few measurements and we calculate a divert to bleed off the excess thrust that we don't need. So it's a 3.64% divert. And then we do a little touchdown prep, which is basically a settling maneuver. We're trying to kill those gyroscopic rates and keep it as upright as possible to have the best chance of landing. And so those are all of the states that the rocket goes through. And of course, we have states that aren't shown here. So that would be like an abort state. If I ever send the abort command from the ground, we can beam that to the rocket, or the rocket can decide to do it itself. It'll pop the parachutes out, it'll move to an abort state. And you never really want to see it, but it is pretty cool. It turns the whole thing red. It is pretty cool. So we'll watch this one more time. You can also take a look at some of the other data or the other pieces of data that are showing up here. You have vertical velocity on the right, altitude. If you look at position and velocity in the bottom left, you can see us sort of move. We end up going about 10 meters downrange. And then you can see the thrust curves and the accelerometers as well. And of course, this is played back. The whole flight is like 9 seconds long. So this is played back very slowly. Okay, great. So that's that. Okay, Kalman filter. Raise your hand if you've heard of a Kalman filter before. I can't see anyone's hands, so we're going to assume like maybe 1 or 2 people have, and we'll try to cover it in a really simple way. This is one of the more important things that I ended up working on with software for the landing stuff. You need to be able to measure exactly where you are to make decisions about how much you need to divert the rocket to bleed off excess thrust. You need to be able to measure exactly what your orientation is, exactly how fast you're moving. You need to know a lot about your situation. And the problem with this is that many sensors return data that's really noisy or very slow. So right here, what you're looking at is a data plot, again, time on the horizontal axis, and then we have speed in meters per second, that's velocity. This is the GNSS XVEL-MS. It's not a very catchy name, but essentially these are the GPS readings. And so the GPS is saying, I think this is our velocity going up and down. And so right here, at 3 seconds, we're up to almost 10 meters a second. And then at 6 seconds, we're down to almost negative 15 meters per second. So you can sort of see the flight profile here. And you can also see the problem, especially if a lot of the GPS or barometer data looks like this. It's noisy, it's slow, and And it's not entirely accurate. There are actually, I mean, we can address this later. There are a lot of accuracy problems with this data as it is. But how do you compensate for this? What other sensors could we use to try and correct for this noisy and slow data? Because if we were to do a running average, right, that data is going to be slow. It's not going to be representative of where we actually are. So what's a really high-speed sensor that we could use for this? What about an accelerometer, which does not measure velocity, right? The accelerometer measures acceleration, but velocity is the integral of acceleration. Acceleration is the derivative of velocity. Getting into math here. But if we take this acceleration data and we integrate it over time, we'll get our velocity on the rocket. And as long as that acceleration data is pretty well accurate, pretty well calibrated, this is actually the real data from the flight here. If it's pretty accurate, we could come up with an estimate of how fast we're moving, right? And we could probably use the noise from like the known noise profile of the sensor to have a good idea of how accurate that data is. Like we could quantify that. And so what ends up happening in a Kalman filter is we use these external sensors that may not be directly correlated or directly responsible for the measurements, but they definitely have some correlation with the measurements that we want. So we want to know what the velocity is. If we integrate that accelerometer and keep track of how noisy that sensor is, we can get a pretty good velocity estimate. And that's what we have right here, all the way down to us going up a little bit, having that little hop. We have a little bit of positive velocity at the end of the flight. And you can see that this data ends up being a lot faster. The GPS reports slowly. We're only coming in at like 4 hertz of update rate here. But if we take those accelerometer readings and bring them in, this is really smooth data that we can work with. PID controllers, this is a slide from last year's presentation. Whether you saw it in Tucson, Arizona when I presented, or saw it online or didn't see it at all, I'll do a really quick overview. A PID controller is not a physical thing. It's sort of a set of math, set of equations that you can use to try and control something. So, the example that I use a lot is trying to control the angle of the rocket, right? With, your rocket is at 10 degrees. How do you know what gimbal angle to set so that you can come back from 10 degrees? And so it ends up being pretty simple. If we have angle on the right side here, we can do some math on that angle and then come up with, an equivalent thrust vector control mount angle to correct for it. So we have a P term, which is directly proportional to that whatever we set here as a number, we just multiply it. So, it's 0.5 proportional to the angle. If the angle is 10 degrees, the resulting value will be 5. The integral, that's the I term of PID, the integral takes the error over time. And so this is usually a pretty small value that helps us correct for misalignments, can correct for a whole host of things. And then the D is the derivative. We take dx over dt, which is the derivative of the angle. You could also feed in the direct gyroscopic rate. That would also be the derivative of the angle. We multiply that by a small value, and we add all those things together, one big PID soup, and then we write that to the TVC mount. I don't know why I use the term PID soup. Anyway, the PID is a super common thing in control systems. You see them everywhere. Honestly, again, with the smart fridge, your smart fridge probably has a couple of PID controllers running to try and control the temperature inside, or the ice maker in your fridge probably has some type of controller like that. It could be something different, but this ends up being a big part of the stuff that I do. So I wanted to show some data about that as well. So this is the orientation around the z-axis, which in all of the footage that I have shown, that's the axis that we're really seeing wiggling back and forth here. Excuse me. So when we launch, we're really close to 0 degrees. We do pitch over to 5 degrees a little early. That's just an alignment error on the TVC mount. But then you can see that we set the set point. That's the yellow line here. That set point gets set so that we pitch downrange a little further. We're commanding it to go there. The gains, which is like sort of the sensitivity of the control system, were pretty low on ascent, and then they jack up really high for the descent, for the landing, because that needs to be a lot tighter control. So then this middle section where we go all the way up to almost 35 degrees, that's the uncontrolled phase of flight. And I say uncontrolled, but truly we have these fins that pop out, around this part of the flight. Once those fins pop out, they bring us back to around 0 degrees. Then when the motor comes back up to thrust, you can see we follow this set point. This yellow set point gives this beautiful little sine wave. And because our control system is really dialed in on landing, that pitch looks kind of wild on the footage, and it looks like, oh my gosh, this isn't well controlled. It actually is. This is very close to what the simulations show. We cut it off a little bit early because there are a couple other phases of the settling maneuver that we want to hit. But basically, this is a PID controller that's trying to track this set point. It's trying to command the rocket to exactly 15 degrees negative and exactly 15 positive. And of course, we don't exactly hit it, but it's quite close. We can also see PID control at work on the velocity reading. So this is the horizontal velocity. And it gets a little easier to understand if you think about it from that camera angle again. So we are 0 velocity on the launch pad, obviously. But then when we take off, when we lift off, we have that little bit of an angle, and we start sliding down range. So we slowly accumulate this velocity up to about -3 meters per second. And then when the motor burns out at T plus 3.5, we're just coasting, right? There's nothing to change our velocity. We don't have a whole lot of control over that. Then when the motor comes back up to thrust, it does an initial maneuver to try and bleed our velocity off. So that's what this big dip is. And then we do our sine wave divert with a settling maneuver at the very end, where we try and cancel all that velocity. Now, here is where a clear discrepancy exists. So you can see at the very end of the burn, we are at like 0.25 meters per second, not squared. This is really slow. Like if you think about it, this is a meter or something. Over the course of 1 second, if we're sliding 25 centimeters, that's nothing. But that's not the case. You've seen this footage. We're sliding like 2 meters a second in that, which is obviously too much because then we tip over. So if you see how spiky this data is, it's a little too much to get into, at least without someone asking a specific question about it. But essentially, the GPS antenna was very noisy on the day. High definition cameras are very noisy with radio frequency, and they mess with GPS quite a bit if you put the antennas too close together. And so the GPS tricks our rocket into thinking that it's not sliding very much. So from a control systems perspective, the rocket did a really great job and thought that it was about to touch down successfully because it didn't know that it was sliding as fast as it was because the data coming in was bad. We can look at a couple more plots here just to address like how the rest of the flight went. And then we're almost done and we can take some questions here. So obviously this is the vertical velocity profile here. So we go up to about 10 meters a second, go down to a little bit less than that. And what we're looking at here is a 0 or a 1 on fins deployed. So this is the command that the flight computer sends to the fins to deploy here. And then the logic that I have to retract the fins is once we are past apogee and past the peak vertical velocity, as long as it's a complicated statement, as long as we are below -4 meters per second, we put the fins back in. So if we never made it below 4 meters per second, the fins would have still been out. And so you can sort of see it happen here. This is the same clip that we saw earlier, but the rocket goes up, and if you watch those sparks, exactly as those sparks go from going down to going back up, the fins come out, and then they go back in as soon as we cross over below -4 meters a second. So that's sort of the logic that's going on with this. 1 second, here we go, and in they go. Wonderful. This is the leg deployment logic. So this is the vertical altitude. Vertical altitude, that's redundant, but this is the altitude of the rocket on the blue line here, and the green line is if the legs are fired or not, if the legs are deployed or not. So when the green line goes up, we're actively trying to deploy the legs. These are deployed based on if we are below, I think it's 6 meters, we fire them, but you can see that they actually end up deploying much lower because it takes about a 1/4 second for that nitrum wire to heat the rubber band up and for those legs to deploy. So, we're firing it like a quarter second before they actually deploy. And when they actually come out, it's closer to about 2 meters above the ground. So that's this onboard shot here. And then I think we have just one more plot, which is the motor ejection sequence. So this blue line is the acceleration, that's the thrust curve of the motor. And we don't immediately eject that motor. What we end up doing is waiting for it to settle a little bit. If you saw the internal cameras, the motor has a lot of wiggle to it. It has a lot of natural, the natural frequency of the motor is powerful. So it wiggles around a little bit. And to ensure that I know exactly how this thing is going to deploy, we give it about a half second before we kick it out. And so this is the ejection progress. It's sort of a complicated, it's a tightly timed sequence where we slam it against the ejection pin and then we retract it before the landing motor can interface with the ejection pin. It's wild. And then you can see the acceleration spike when it happens. So here's the internal view. We have a motor. This is a camera that's actually on Ava, on the flight computer, pointing down at the thrust vector control mount with some little internal LEDs. And so you can see the motor kick against that ejection pin and then slide out. So these are all synced up. I'll let it play 1 or 2 times here. You can also see that motor hat. It was really tough to get these wires to not mess with the motor mount. These TVC wires are difficult to do cable management on. It would have been a lot easier to run these wires on the outside of the rocket instead of the inside. So that's that. And then, I wanted to talk about this too, because I didn't do a good job explaining it. And then we can take questions. So what you're looking at right here is a simulation of the flight. And this is a simulation if we don't do any type of throttle maneuver and if we assume that all motors perform the same. So we go up to 30 meters. The red is our altitude here. And if we fire the landing motor a little bit early, what are we going to do? We're going to land a little high. We've got our velocity measurements here. This is thrust. This little gray line is drag as well. And then we have altitude. So if we fire early, we're going to land high. If we fire late, hold on, let's see if I can line this up. If we fire late, we're going to hit the ground, right? So what if we fire the motor a little early always, right? This is how we end up doing the throttle invert. If we fire the motor a little early always, and then we pitch back and then forth to sort of cut out that horizontal velocity that we create, but we fire the motor, we change the amount of the motor that we're firing vertically into the system, we can effectively throttle it. So you can see this velocity curve. We have these 2 little dips here. That's what we're doing when we're wiggling side to side, back and forth. And then if I let this clip, if I scroll through here, you can see that on almost every time, as long as we have a good enough measurement and good enough certainty of where the vehicle is in flight, we can do a pretty good job of getting to the ground safely. Each time it's about a meter. We're changing the descent curve. We're sort of changing the radius of that descent curve. But we can end up, landing about a meter from the ground each time, even if we randomize when we light that motor. So, we spec the flight around the latest that the motor could possibly come up to thrust, and then we work the rest out with the flight computer in real time, as long as we have a good measurement of where we are. So finally, I want to address the major changes that are coming up before the next flight, and then we can take some questions. So one of the biggest ones is going to be changing the placement of the GPS antenna. I only mentioned this briefly, but the GPS antenna was mounted on the side of the vehicle, right next to a couple of the high-speed cameras that are on board. And the RF interference messed with that antenna quite a bit. So we're going to have to move the antenna a little higher up on the vehicle. And I've sort of been on a rocket break for the last month and a half or so, so I haven't gotten around to it. It's an easy change, but that's one of the biggest ones. Improving the pad leveling is another big thing. I said earlier that you can, in theory, do this with just an inertial measurement unit, and that is what improving the pad leveling is about. If we have certainty that we are upright on the pad to within about a 1/4 degree or something like that, over the course of 10 seconds, our velocity estimates just from accelerations alone are not going to drift enough to cause us to tip over. So if we can improve the pad leveling and get the GPS where it needs to be, we should be well within capable of nulling out that last bit of velocity before we touch down. And then finally, the other glaring error is the landing bounce. So when the vehicle touches down, this spongy grass, just all it wants to do is take in the energy of the rocket and put it right back into the rocket so it bounces back up. And what we need to do is absorb it. SpaceX does this with aluminum honeycomb. They do a crush core, that's what they call it. And so you need to absorb the energy into the system somehow and radiate it as heat or sound, anything like that. You need to radiate that energy as something else. And a crush core seems like an interesting idea to pursue for something like this, so that we can, almost like a dead blow hammer, just stop, completely arrest the movement when we hit the ground. I don't really want to use spikes. I kind of feel like spikes in the legs is A, cheating, and B, a little dangerous. Like, I don't love the look of trying to land a rocket that could impale you a little bit. So we're going to try to not do that. And so with that, that is my presentation. And looks like we're coming in at just about 52 minutes, which is great. So now, if you guys want, I think technically someone can confirm we should have mostly unlimited time to do questions. So I'm going to try to take those in the Q&A section. And yeah, let's do it. Oh, well, I'll take Tom's question first here in the chat. Would flying over pavement greatly reduce bounce? Yes, it would, Tom. Yeah, this has been suggested a couple of times, and I'm always really scared to do it. The downside of flying over pavement is that if you have a bad flight, you're going to have a worse flight because you're over pavement, and you're going to scratch up your paint. You're going to come down a little harder. And so the benefits of a hard surface like that also have some drawbacks. And especially with something as experimental as this, I'm going to try to avoid pavement as long as I can. We'll do some tests to think about that, to evaluate that before we fly again. Okay, going from the top here in the question and answers section, Sierra Mike asks, what are the antenna considerations for such a project? Patch, helical, other. Great question. Okay. If I say answer live, will it do anything crazy? Okay, great. There we go. So I use a helical antenna for the GPS. I think you could get away with patch antenna or like a ceramic patch for GPS. I use a monopole antenna for the telemetry. We're not going high enough that we end up at either of the poles or either of the dead zones, or like the polarization pattern. And then we're not flipping out of control enough that a patch antenna would lose full track of the sky. So that's that. What is your stability margin? Well, the aerodynamic stability margin is negative or 0. There is no aerodynamic stability on this rocket. I actually don't know what the stability margin is on the fins. It's certainly stable under those fins. And then I don't have a good number for you on the control system analysis of the stability margin there. Sorry, Pat. Let's see, here we go. GNSS altitude solutions are noisy. How about using radar instead? Good question, Cliff. So GNSS altitude data is noisy, indeed. For radar, the issue is that you have to always be pointing at the ground. You have to have that, is it a transmitter or radome? You have to be pointing that out at the ground. I do have a LiDAR sensor that I use for a hopper vehicle, sort of a UAV. That worked pretty well. But just through acceleration data, GNSS altitude, and barometric data, I do believe I have enough accuracy to accomplish what we need, within 0.1 meters or so. Okay, cool. Uh-oh, it's kicking questions out, or it's, oh, wait, am I answering them in the wrong order? Is it bottom to top or top to bottom? All right, I'm just gonna pick random ones. Gary asks, are there launch constraints for wind? I should also probably stop sharing my screen. Here we go. Screen sharing. Okay, hi everyone. Are there launch constraints for wind? I usually try to not launch if it's greater than about 10 miles an hour, and I usually launch at dusk, so that's often even less around then, and then I'll wait for a point that doesn't have a lot of wind. Let's see. Guy asks, is the 2-motor TVC gimbal mount completely different than your original mount, or is just the motor tube replaced? Great question. The mount is entirely different. It's a totally new design, and yes, that's the answer. Is Ava available for sale, or will it be? Are your Signal R2 kits still being sold? Thanks, Erza. So Ava is not available for super public sale right now. There are some concerns about like the export control factor of selling Ava. So I've given it to 1 or 2 people that I really trust to fly it, and that's sort of where it sits right now. For Signal will have another round of sales, I believe, this spring, maybe late this spring, and then we're going to try to start working on the successor to Signal at that point. I have some ideas about that, but I don't have enough information to like feel comfortable sharing it yet. Okay, here we go. Joe, did you write your own Kalman filter? Did you use an off-the-shelf library? And if so, can you recommend one? Gordon, I wrote my own for this one, and on the Hopper vehicle that I mentioned before, this little UAV thing, if you look it up on the BPS YouTube channel, it's called Sprite. The Hopper one used a few instances of Tiny EKF, which is this great, it's totally free and available. There's one on GitHub. Tiny EKF is in a little extended common filter, super lightweight, really fast to run, and it is a C++ library, so it'll work with a lot of embedded stuff. But I did write my own for Ava. What is the plausibility of a 3-engine TVC mount for a model Starship? This is what I am working towards. Is it a viable roll control method? Well, 3-engine TVC will certainly give you roll control, just like 2 engines will. Like the Atlas V has 2 engines that can gimbal, and that's how it controls roll. 3 engines by that effect will also do it. I don't have anything like that in the works. Starship is a really hard thing to do at the model scale, not just because of the aerodynamic control, but if you ever want to land that thing propulsively, that's a very hard problem to solve. I'll put it that way. Are your state machines mealy, Moore, or a combination? Do you have nested states, hand-coded, or FSM framework? They're hand-coded, Paul, and I do not know. I do not have. I think I have some nested states in. If I understand the question correctly, I think I have a few nested states in the idle mode. The idle mode is actually like 4 or 5 different modes, depending on what section of idle we have. Those are kind of nested. And then I do not actually know if they're mealy or more. Sorry. I don't know the definitions of them. What code or compilation, I guess it is compilation, system are you using to manage state? It's all written in C++. It's not like a specific system, really. The states are numbered, so they're sequential. I can just do state ++. And that allows for a lot of flexibility. You could also do states as an enum, and that would work fine. And then I think if for compilation systems or compiling stuff, I use, it's all still technically Arduino. I write in the VS Code IDE and then use Platform IO. They have a little plugin for it to interface with a lot of the Arduino compatible boards. Okay. What do you use for these gorgeous data graphs? Thank you, Nathan. I can't take any credit for it. It's based on the Grafana GUI, but it is, that's the back end, and then the front end is built by this company called Curve. If you guys are familiar with Launcher, they're doing these tiny rockets out in New York. They spun off a little company called Curve. If you go to getcurve.io, that's what I use to visualize. Totally free and really beautiful data. Really beautiful plots. Okay, we're burning through these questions. This is great. Curious what methods you consulted in designing that wheel for roll control. Theo, great question. You're going to expose me, though. So I just sort of like took the first design that I thought, maybe this will work. And then I put it on I suspended the rocket on a rope, and then I just started testing out like gated PID values to see what worked. And it was good enough that like the criteria for success for the roll wheel is that we just can't have a high roll rate. If we roll 90 degrees, the control system does not care, and it will totally compensate for that. We just have to not have a high roll rate. So the wheel is like janky and not like I did no proper analysis on it, no proper design. I sort of stuck it on a string. It seemed to work well enough, and I was like, great, let's fly it. That's the analysis of that. What 3D printed filament material are you using for the motor mount to handle the motor heat soaking through the paper case during the burns? Awesome question. I meant to address this in the presentation. So all of the printed parts are PLA or polylactic acid, which is like objectively one of the lowest melting plastics you can do. And so what I do to mitigate that is that motor ejection happens as soon as we possibly can after we do our ascent, right? So the rocket goes up, and then that heat isn't totally soaked through to the outer edges of the cardboard yet. So like we can take advantage of that and just be like, okay, goodbye, get out of here, motor. And that's pretty much what we do. It's just they're short firing times, and then we ditch the motor as soon as we can once it's done burning. Why not use the ascent motor's ejection charge to eject it? A spring-loaded motor clip would then keep the descent motor from ejecting. Joe, great question and nice name. Also named Joe. The reason you don't want to do that is I'd be worried about sparks going everywhere. And I guess you could use the ascent motor's ejection charge, but you still need a way to get the landing motor into place. And you cannot fire the landing motor deep within the tube. You will get what's called the Krushnik effect, so you lose a lot of thrust. Interestingly, you could, I mean, it's a chaotic process, so it would be hard to characterize, but interestingly, you could use that to throttle, to do a little throttle control, is take advantage of that Krushnik effect if you fire the motor deep in the tube or if you even actuate it forward or aft. How do you know if you have GPS lock? Is there an RF telemetry link? Yes, there is, Gary. So we have a 900 megahertz radio. It's a little XP radio on the rocket, and then we have the same radio on the ground connected up to a computer with the little ground station terminal. And so I just read out the sensors and like take a look. The vehicle will arm itself and be all the way ready for flight. So even if we didn't have that connection to the vehicle, we could have confidence that it's ready to go. There's a lot of self-checking stuff on there. As Ava starts getting ready for like higher power flights, if we don't have immediate access to the flight data, we need to know that the computer's ready. And so some of the pre-flight stuff before it will arm itself and say, I'm ready to launch, is GPS lock checks. And so it just will not get itself into that ready state if it doesn't see that we have good lock, a low PDOP or low high degree of precision. We have to have real latitude and longitude data. We can set constraints on that too. And then there's like 5 or 6 other things that we check for just in the GPS alone to make sure we're ready to launch. But it's also easy to just look at the telemetry and be like, oh, yep, you got like 10 satellites or whatever. How do you recommend people get into flight computer coding? I want to get into it, but not sure where to learn. I identify that with that for sure. It's really like there's not a lot of books on it. There's not a lot of resources. I'll go ahead and plug my own channel, bps.space on YouTube. I do have some videos, but a great project to learn flight control with is a self-balancing robot. I never ended up doing one. Hold on 1 second. I never ended up doing a self-balancing rocket, but they are great projects for learning about feedback control. So that's one thing that you could try. Okay, here we go. Oh man, all right, another question from Guy. I have almost 30 BPS TVC flights under my belt using F-15s, and getting enough altitude is problematic due to the rocket mass. Would the 2-motor mount theoretically work if both motors are used for ascent? Yes, they would, Guy. You would lose about a half a second of active control and probably a full second if you factor in the delay between ejecting and the delay of ignition to motor come up, or like motor peak thrust. So if you wanted to, you could definitely do a 2-stage flight, but the only stage that you eject is the motor itself. That would be a fun thing to try. But nothing is really set up for it right now, and the motor mount is quite fragile. So it will need some work before we do anything like that. What's your CG on touchdown? Have you considered altering the CG of the rocket on descent to be lower to the landing legs to help stick the landing? Peter, yeah. So this is a really interesting problem because the higher your CG is, the more control authority you have. And if you have to do a really intense divert maneuver, you want a high CG. But the lower your CG is, the more stability you have on touchdown. So it's a total trade-off. My CG is about 20 centimeters up from the bottom of the rocket. It's very, very low, nowhere near the nose at all. So it actually is quite low. We're just also sliding very fast. Excuse me. Joe, have you thought about moving the retro motor up and down in the tube using Krushnik effect to throttle it? Chris, I think you asked this before I answered it, but yeah, I think Krushnik effect throttling could be a really cool project. There are a couple of people I know who want to pursue that as well. It is a chaotic process, so you will have to do a lot of characterization of how that throttling changes throughout the burn. But I would love to try it. I would love to see someone else try it. Totally a viable option. And especially with something like one of those Aerotech G8s or G11s, some of those super long burning motors, you could hover a rocket with that if you get it working. Harlem asks, have you considered some type of crumple zone similar to the crush core on the F9 landing legs to prevent any bounce? Would it not be practical at the scale? No, totally practical at this scale. It's definitely in the maybe this should be a thing I add pile. I think it's something that I'll probably end up testing in the next few weeks or months. Okay, does the second engine have an ejection charge as well, or is it plugged? I have plugged both motors. Technically speaking, I don't need to plug either motor. Although, I mean, you wouldn't want to fire the second ejection charge, but you definitely wouldn't have to plug the Ascent motor if it was a 4-second delay or greater, because you just eject the Ascent motor before the delay goes off. Is that a good idea? Probably not. You know, it's already sketchy enough to be ejecting a still delay charged motor burning thing out of the back of the rocket. So I'd probably keep removing the ejection charge, but technically you don't have to. Okay, I think this might be a duplicate question. Let's see. A good amount of people have been inspired by you. There are now 13-year-olds pursuing thrust vector control successfully. What advice would you tell a younger person trying to do what you do? I don't mean to sound condescending, but be really patient. These things are crazy hard. People spend their entire life perfecting control systems and working really hard at, you know, getting good at electronics or getting good at software engineering. You know, like if you tackle a project like this, you're tackling so many facets of things that people will specialize their entire lives on. So when stuff doesn't work, it's easy to be like, this is garbage. I'm giving up. So my advice would be patient. I am 5 years in now and still like wish I was 10 years in, or like I'm 5 years in and still like get a lot of things wrong all of the time. And also, I wish people would pay more attention to safety. I see a couple of projects every now and then where people are trying something similar and there's less attention paid to safety. And like I did that, I wasn't very safe when I started, but you know, like you can only get lucky so much, and at some point someone's going to get burned. And so safety is always a recurring topic at NARCON, and you know, with trying to figure out how do we make sure that people getting into the hobby don't mess things up. But safety is a really big deal, and I'd still love to make a video or some type of resource on how you can, you know, do this stuff and not burn your face off, which is, you know, a thing that you want everyone to achieve. Okay, would you consider flying some kind of basic guidance system, selling some kind of basic guidance system kit to raise funds? I think, Steven, I don't know if you are aware. Sorry, I actually do that. I started doing that like 2 or 3 years ago. And so I do sell a guidance and control kit called Signal. And so you get a little computer, a little thrust vector control mount with the servos and everything, and then you get instructions that tell you how to build this thing and, you know, get out to the launch pad. It is not like constantly for sale because I'm doing a pretty bad job of like keeping it in stock. But we're bringing at least one person onto the team this year to like focus on that. And so that should be back in stock pretty soon. Okay. Have you had any experience with CFD simulations? Not that much until just recently, and I can't talk about it. Sorry, it's a little it's a secret project. Okay, here we go. Could you use a leg shock absorber that used a variable vent on shock absorber? I think that may be similar to the crush core question, but yes, we need some type of shock absorber that doesn't that truly absorbs the shock and dissipates it, like a shock dissipator, not just absorber, because it can't get put back into the system. Okay. I would love details on propulsive landing and the safety code, specifically on fire prevention. Also a great question, Erza. So there are like 10 different things that we check before we fire that landing motor. You know, I mean, obviously before the flight, I live in Tennessee, so the environment that I live in is always very humid. There's an extremely low chance that, given the burn time and given the time of proximity against the ground, that the rocket will light the grass on fire. Of course, I always bring a fire extinguisher to the launch site. It's a Class 1 rocket, well within the limitations, and so you know I can launch this in an empty field. And as long as the ground is reasonably damp, the grass is reasonably well grown, there aren't, like, I'm not super concerned about fire safety with that. I mean, I'm concerned about it, but I'm not worried about that becoming a reality. For ignition commitment, I think that was the second half of the question you asked. For ignition commitment, that was one of the 10 things that I mentioned. Like, there are a ton of checks right before we light that landing motor. So some of them are, where are we? How high are we? What angle are we at? What angle will we be at, given our current gyroscopic rate, if we light the motor and it takes 0.7 seconds for it to come up to thrust, and we're at 0 degrees, but we're rotating really fast, we know that by the time the motor comes up to thrust, we're going to be out of bounds. So it ends up being a really dynamic, like, if statement. I mean, it's a bunch of them, but it's a bunch of if statements of, like, do we pass this criteria? Do we pass this criteria? Do we pass this criteria? And because, you know, these are fast microcontrollers, we can run that really, really quick and then say, if we do, yes, light the motor, or if we do not, if any one of those things is incorrect, we pop the chutes and we safe the pyro channel. So there is a decent amount of consideration for making sure that we don't light the motor when we do not mean to. And then, of course, there's a physical arming pin on the rocket, which doesn't get connected. We don't have actual continuity on the channels until right before launch. There's no like physical possibility of sending current through that second motor until we are on the launch pad. Why not just put a 4K camera on the rocket and store the video in a memory stick instead of transmitting it into the ground? Hey, Michael, so maybe I didn't do a good job explaining it. I don't transmit video to the ground. All of the videos that you're seeing here with the live telemetry stuff, that is footage overlaid. And so there is a 4K camera on the ground, and then the rocket has actually like 4 different cameras on it that record locally to memory cards that I go in and I take those cards out and view them after the flight. So the only thing we're beaming down to the ground is actual flight data, like numbers. What's the clock speed of your processors, asks Ron. The central processor is 72 megahertz. It can be overclocked to 96, but it's not really necessary. And then the sub-controllers, so the navigation computer and the telemetry computer are both 48 megahertz. And yeah, that's it. Let's see. Would thin sound deadening material like Vibrablock or Dynamat work to help with the landing hop? I do not know, John. That's a good question. I do not know. I can tell you that we don't have a good idea of exactly where we'll land, though. We have a very large landing dispersion zone or landing probability zone. We cannot, because we do this throttle maneuver where we go back and forth, we can't actually predict exactly where we will land. We just know that we're going to be within a certain corridor of landing spots. Okay, here we go. Keep going. Can TVC be used for rocket planes? It totally could. You could absolutely do that. It would be, yeah, I see no reason you couldn't. I mean, they use TBC on fighter jets. To be more clear on my question, after you're done with the thrust vectoring, could you mechanically drop the CG to get the best of both worlds? Oh, right, Peter. Okay, understood. Yes and no. Yes, you could theoretically do it. You could move the flight computer down, especially if you're done with TBC. But you'd have to do it really fast, because if you're a meter above the ground, I think theoretically you could. I think practically it would be a lot of work. Could Signal be used with aerodynamic control surfaces instead of TBC? David, I'm afraid it could not. Sorry, it's only built for thrust vector control. And aerodynamic control ends up being like a few times harder than TBC because of, it's just a very dynamic flight profile when you're doing aerodynamic control, because your control forces scale in all sorts of ways with your speed and your AOA. Signal can't do it, sorry. Where does BPS go after you land? Excellent question. That sounded sarcastic, sorry. It is a good question. Robin, so this year I'm doing high power. The landing stuff is gonna happen one way or another, whether it's this year or next year, but I've started purchasing parts for my level 3 build. I've completed my level 2, and so I'm going out to a very remote area, and hopefully in about April, flying my level 3 to aiming at 10 kilometers. It will be passive control with pitch and yaw, and then an active roll control wheel on board, culminating in, I think a couple HPR flights this year, and then aiming a lot higher in the next few years. Okay, almost there. Couple more questions left. A lot of questions. Do you ever cover Maker Faire events? I have not gone to any Maker Faire events, but and I would like to, although I can't quite do that right now. I think that would be fun though. Okay. Here we go. Is integrating a processor like the here we go, MIMXRT1062 from the is the TNC 4.1 into a flight computer worth it if you are making a large amount of them? Yes, but you wouldn't want to do it for, it is worth it, but you wouldn't want to do it for the TNC 4.1. For Ava, it's essentially a TNC 3.2. It's the Mark 20 DX256 VLH7. I know it by heart at this point. It is, the central processor of Ava is a TNC 3.2. It does make sense if you're building a large amount, but also consider that you will still have to buy the bootloader chips, the bootloader flash chips from PJRC. So, that will always be a fixed cost for you, unless PJRC can give you a crazy deal on them. Okay. I think I know how to solve the bounce problem. What if you made the legs so that they could just barely hold up the rocket? Then when Scout touches the ground, it doesn't hit the ground, it just melts into the ground with the motor touching the ground. Well, I mean, maybe. I really don't want to put things on this rocket that can only work once. This is the same design philosophy that SpaceX uses, and a lot of newer aerospace companies try to ditch all of the pyrotechnic devices so that everything on your rocket can be tested on the ground with the actual flight hardware. And so legs that destroy themselves each time you land feels it feels like the antithesis of that. Okay, have you considered upscaling to higher power motors? Asked Stephen. Yeah, so that's coming this year. It should be pretty good. And I'm not going to do thrust vector control immediately with those. The stakes are a lot higher, both financially and personal safety-wise. But we're getting there. We're getting there. I want to do it responsibly, so I'm taking it slow. I'm also working on a model Starship. Do you think an F-15 would be a long enough burn time to complete the flip landing? It would require 2 for each part. Would it be best to use first aerodynamics? Impossible. I would say I cannot answer that for you, but my answer is almost certainly no. I'm not going to tell anyone to not do any projects, but Starship is such a crazy hard thing to do already. Bringing it to the model scale is going to require like a PhD's worth of work to get that to work. I would say try to address one problem at a time and fly. Like the aerodynamic profile of a Starship would be a fun thing to try and fly. I think it may you may be biting off an amount with that project that will be frustrating to you down the line. Bob asks, how about landing on a sticky surface? I think that would work. I also feel like it's sort of cheating. I really want it to just touch down gently as if it was touching down on a regular surface. And a sticky surface feels like, you know, I want to get the control system good enough that it can really, like, you know, stand for itself. With legs, Michael says, legs that go back with springs. Well, the problem with springs, I guess they would dampen it. I don't know. I'm convinced that I don't need springs, but some type of crush core would be good, I think. Would landing on a surface like sand be beneficial? It's not springy like grass, but it could definitely absorb because it can deflect. Okay, yeah. A surface like sand would totally work. But again, because we can't control exactly where we're touching down, I'd need to bring a lot of sand to the launch site, and my local RC club is probably not going to be thrilled with me doing that. Alternatively, I could fly it at the beach, but saltwater corrodes a lot of things, and I don't want the potential for this thing to go into the ocean or a pond. And it also feels like I can still, I know I can get this to work if I'm careful about how the legs absorb the energy. Yeah. Okay, and then finally here, Bernard asks, I keep thinking that concentric tubes for the leg support struts just tweak the friction between them to allow them to collapse enough. Then you pull it back out after the flight. That is a good idea. That's a legit idea. I mean, that's the same thing as the crush core. You are spending the energy as friction and heat and a little sound, right? And they don't have the possibility of coming back up. And as long as the tubes are vented, you don't have a column of air that's pressurized to put it back into the system. That's a cool idea, Bernard. I like that. I think machining something like that or getting the tolerances right would be a little tough, but a totally workable problem. That's a great idea. I like that a lot. I'm going to take a screenshot of that. If I end up using it, I will credit you in a YouTube video. All right. Well, folks, that looks like all of the questions in the Q&A column. I want to thank everyone here for joining and spending your time, choosing to spend your lovely Friday afternoon with me. I hope you enjoyed the presentation. I hope this was fun to watch. And yeah, I look forward to seeing the other presentations later this weekend. I think it's going to be great. And there's some really cool stuff. So thank you so much for joining me. And that's that. Now, I was told that the stop broadcast button stops things a little early. So if I just get cut off, don't be super surprised. Let me make sure that I don't get super cut off here. And stop broadcast. Are you sure you want to stop the broadcast? I am